We have learned problems in year 9. Okay, so first one is just exploring. We have a revise on what we have learned in year 9. So a problem is a graph of a quadratic relation. So what is the quadratic relation? Which is ax squared plus bx plus c, or something similar to that. This is called a quadratic relation. Y is equals to square x squared, some x or some constant. The only requirement is a not equals to 0. So b can be 0, c can be 0, but like a cannot be 0. You must contain some x squared in your equation. This is called a quadratic relation. So if it's a quadratic relation, your graph will definitely look like that. Okay, your graph will definitely look like that or upside down. So this is the simplest rules. Okay, graph, which is y equals to x squared. Y equals to x squared. That's the simplest rule. So that's a standard graph. Let's say that's a standard graph. The graph looks like that. Okay, if you plot many points, at 0 you have y equals to 0, at 1 y equals to 1, at 2 y equals to 4. After you plot infinite many points, and we can just complete the shape like that. Okay, so what's the key feature of this point? The key feature is we have vertex or turning point, which linear graph does not have. Okay, think about linear. Linear is just a straight line. There's no turning point. There's no vertex. So the first thing we have is a vertex or turning point at 0, 0 for this graph. Okay, which is the minimum turning point. That's a local minimum. And the second one is this graph is a minimum vertex because it's a upright graph. I will have a minimum value. Okay, that's the second thing. The third thing is this graph is symmetrical about x equals to 0. So if I sketch a line here, left hand side and right hand side are identical. Okay, left hand side and right hand side are identical. This is applied to all the quadratic graphs. Every quadratic graph will be symmetrical. Okay, will be symmetrical. I'll talk about more which line they were symmetrical about. It's not always the y-axis. Sometimes there's some other vertical lines, but in this case, it's x equals to 0 will be the symmetrical line. And the last thing is we have x, y intercept and turning point all at the point 0, 0. Okay, x, y intercept and turning point all at 0, 0. Well, for some other quadratic graph, it will be different points. Okay, so x intercept, y intercept, turning point, they're all different points. So in this graph, we have all 3 points at 0, 0. Okay, so that's what we can see from this graph. It's very different from a linear graph. Has its own shape. The shape is symmetrical. This shape always got a turning point, and we have x, y intercepts. Okay, so we will think about we won't always sketch x squared graph. We will try to sketch some graph with transformations. We stretch that a little bit. We shift it left or right, up or down, or we can reflect it. Okay, we can reflect it. Let's have a think. We can do 3 things. One is dilation, one is reflection, and the last one is translation. Okay, we can do 3 things basically. Dilation, reflection, and translation. So let's just have a think about dilation first. The green graph on mine, you can see the green one is 2x squared. The red one is the standard graph, which is y equals to x squared. And the blue one is a half x squared. What you can see from this? What you can see? Clear?
You can see that the higher the number, A is the more narrow the graph is.
Yeah, the narrower the graph is. Okay, so the A value will decide whether it's a narrow graph or wider graph compared to the basic graph. The basic graph is y equals to x squared. So the larger the number, the higher the graph. Okay, the larger the number, the narrower the graph. Okay, it's very narrow. So 2x squared is narrower than x squared. Okay, and they all meet at 0, 0. This is dilation. The second thing is reflection. Okay, reflection. If you have a negative in the front, see the green one is negative x squared, and the blue one is negative 2x squared. Okay, if we use the thing we know from the previous graph, so the larger the A value, the narrower the graph, right? The larger the A, that's what we said. The larger the A value, the narrower the graph. Let's compare -1 and -2. Which value is larger?
1.
-1 is larger. Then according to what we have said, -1 should have a narrow graph. Is that correct? But it's actually not. Like -1 is a larger number compared to -2, but it's not having a larger, like a narrow graph compared to -2. Why is that? Because when we think about the dilation, we don't think the sign into it, and we don't take the sign into consideration. We just consider about the pure number itself, the absolute value, okay, the positive number. So -1 is basically this dilation is just 1. There's no dilation. And the -2 is there's a dilation of 2 for that graph. So 2 is still a narrow graph compared to the 1. And then we get reflected down. So we'll think about the positive side first, whether it's narrower or wider. Then we think about the reflection. It's like we don't take the negative into consideration when we think about whether the graph should be narrow or like wider. Okay, so according to what we said now, can you just compare? Can you compare -2 for -1/2 and the third? Okay, which, like that's the coefficient of A. Like they all have x squared in the end. Which graph should have, like, can you just arrange them from narrow to the wider? Like which one is the most narrow one and which one is the widest one? The larger the value, the narrower the graph. Okay, so which one will be on the left hand side? 4. Okay, 4 is the largest number, so 4. What's the next? It's 2. Okay, it's the -2. Even though it's negative, it will be reflected to the bottom. We will only think about 2, so 2 will be the next one. And how about the third and a half? Half, so it's -1/2, and the last one is a third. So that should be from narrow to wider. Okay, narrow to wider. That's how we arrange them. Okay, my 4 will be very narrow, and 2 is a bit wider, and a half is quite wide, but like negative going this way, and -1/3 is even further, like in that way. Okay, that's the full graph we'll have. So if I can sketch that on this, so this one will be the x to the 4x squared, and then I will have negative that will be a little bit, I should draw a little bit wider. That's a little bit wider. That's -2x squared. And then we have next one is -1/2. -1/2 x squared. And the last one will be a third, will be very wide. Okay, very wide. Something like that. That's a third x squared. Okay, that roughly like that. If you sketch them, that's the relationship. 4 will be positive and they have like really narrow graph, and 2 will be the next, a little bit wider than that, but upside down. And they have -1/2 is quite wide compared to -2, and then a third is even wider, but it should be like positive shape going up. Okay, upright. Okay, that's what we have, and that's easy to think about dilation and think about reflection. The hardest one to think about will be the translation. Okay, will be the translation. The translation is moving all the points. Okay, like the whole graph will move every single point to the left or to the right or up or down. So all the points will like shift. So let's have a think. What is the turning point formula first? For a quadratic, what's the turning point formula for quadratic graph? Turning point formula. Y equals to a bracket, x h squared plus k minus h. Yep. So x minus h squared plus k. That's the turning point formula. It's turning point formula. Then it's giving you the turning point. This directly gives you the turning point. The turning point will be h comma k. Okay, h comma k. You may haven't learned that before. That's fine. Just write that down. That will be the turning point form. And the turning point of the quadratic will be h comma k. It's directly giving you the turning point. Okay, the next thing we think about is like that. All the points will be shifted like somewhere, like left or right or up or down. Then have a think. The turning point will be shifted as well. The turning point, like we have a graph like that, and we shift it this way and up, and then maybe right a little bit. The turning point will still be the turning point. The turning point will not change. It will change value, but it will still be the turning point. Then let's have a think about this. We have a graph, y equals to x squared. We have turning point 0, 0 for this graph. Okay, so this graph has been translated 2 units to the left and 1 unit up. Okay, can you tell me what the turning point becomes? Like what's the turning point now? Like the whole graph has been shifted 2 units to the left and 1 unit up. Yeah, clear? Yeah, negative 2, 1. So that's the new turning point. Negative 2 and 1. Okay, negative 2 and 1. That's the new turning point. Okay, if that's the new turning point, can you put that into the turning point formula for me? Like what's the new equation will become? So that's the h value, that's the k value. And you know that a equals to 1 because the original graph is x squared, a equals to 1. The a value doesn't change because there's no dilation. So can you tell me what is the new equation for this graph, please? Like turning point is given to you. H and k and a value, you all know about that. Can you just put the values in? Y equals to a is 1, x minus h. So it's x minus negative 2 squared plus k, which is 1. So the new equation becomes x plus 2 squared minus plus 1. Right? Your original equation is x squared. And now your new equation will be x plus 2 squared plus 1. That's your new equation. Why is like that? Because the turning point before is 0, 0. After the translation, your new turning point becomes negative 2, 1. And then we know the turning point formula. That's the h and k value. I just put h and k value back into the equation. And I have the new equation out. And can you have a look, this equation? The plus 2 means moving 2 units to the left. And the plus 1 means you have 1 unit translate up. Okay, so that's how we think about it. So therefore, if we think about this blue graph will be translated 3 units to the left. Because it's plus 3 for x, that will be translated 3 units to the left. Why? Because this turning point here will be negative 3, 0. But before you have 0, 0. Okay, compare the two turning points. What has been changed? Moving 3 units to the left. Okay, moving 3 units to the left. And same as this graph. Okay, x squared minus 3. We have 0, negative 3 as my turning point. What has been changed? Moving down for 3 units. Okay, moving down for 3 units. So therefore, what we can see is, in the bracket, if we add something, we say moving to the left for that many units. If we subtract something, we say moving to the right for that many units. If in the end, after the x squared, we plus something, we said it's moving up. If we subtract something, we said it's moving down. Okay, so this blue graph will be moving up by 2 units, and you plus the 2 at the back. See, the green graph is moving right for 2 units. Then it's x minus 2 squared. Okay, it's x minus 2 squared. That's how we do the translation. That's how we do the translation. So that's the translation step. So we can do 3 things. Basically, it's dilation, reflection, and translation. It won't only have one, okay? It will have like many combinations together. We can have a one dilation, we can have one translation, and we can have one reflection together in one question. So let's have a look at the following graph here. Okay, let's have a look at the following graph here. We have maximum or minimum values. Okay, so say maximum or minimum turning point. Do we have maximum or minimum turning point? So this is think about turning point. For this one, first one, you have minimum. Because it's an upright graph, you have a lowest value. That's a minimum. Okay, whether this graph has been reflected in the line x-axis, yes or no? Has been reflected compared to y equals to x squared? No, it's not reflected. Still positive. Okay, what's the turning point? 0, 0. Okay, good. And when what's the y value when x equals to 1? 4. Okay, 1 squared is 1, and that's 4. Is that a narrow or wider graph compared to y equals to x squared? Narrow. Okay, next one. X plus 2 squared. Do we have a positive or negative, like maximum or minimum turning point? Minimum again. Okay, is that reflected by x-axis? No. Okay, no, not reflected. What's the turning point? What's the turning point? Negative 2, 0. And when x equals to 1, what's the y value? 1 plus 2, 3. 3 squared is 9. Okay, next one. Is that a narrow or wider graph compared to x squared? Same. Yes, good. Same. There's no change in a value. A is still 1. There's no dilations. Okay, will still stay the same. It's only get a little bit like translate left or right. But the graph will stay the same. Okay, for C. Do you have a maximum turning point or minimum turning point? Maximum is upside down. Has that been reflected? Is that reflected? Yes, reflected down. What's the turning point? 0, 3. When x equals to 1, what's the y value? X is 1, y is 2. And do we have a narrow or wider graph? Same again. Same graph. Okay, so that's the revision about year 9. Okay, that's all, everything about year 9. So the next one, we'll try to sketch. Okay, I may not really think about the sketch for today. So if you can, okay, can you turn your page to page 5 for me, please? Okay, what I want you to do is, I want you now to remember what we have learned in chapter 5. So I want you to factorize page 5 and page 6 by cross multiplication, or like any method you like. So I want you to factorize that. Okay, what means by factorize? 2 linear factor times together. I want you to factorize page 5 and page 6. And I want you to, okay, can you turn to page 7? I want you to complete square for page 7 and page 8. Okay, complete square for page 7 and page 8. That's what I want you to do. Okay, so the rest of today's lesson, I want you to spend time on those questions. There should be 8 questions in total. 4 factorized, 4 completing square. If you forget anything, discuss with your friends, or you can come to ask me, trying to pick up that before I really start to sketch graph. Okay?